students, welcome to video lecture on dynamics of machinery. In the today's lecture, we will discuss about equivalent single degree of freedom vibration system session 6. So let us start the numerical on the same topic. A machine weighing 20 kg is supported on two slabs of isolators, natural rubber and felt as shown in figure. The natural rubber slab has a stiffness of 3000 Newton per meter and an equivalent viscous damping coefficient of 100 Newton second per meter. The felt slab has stiffness of 12,000 Newton per meter and the equivalent viscous damping coefficient of 330 Newton second per meter. Find the undamped and damped natural frequencies of the system in vertical direction. Neglect the mass of the isolators. So, whatever the system is given, first of all, you have to draw the mathematical model for the same or equivalent mathematical model for the given physical system. Okay, so equivalent mathematical model can be drawn by considering basic three terms, that is spring, mass and damper. So mass term, whatever the machine is available here with the weight 20 kilogram, so for that the support is given by two slabs of isolator. First one natural rubber and second one is nothing but the felt. So different values related with this natural rubber and felt given with respect to stiffness as well as damping coefficient. Okay, so whatever the mass involved in the system can just represent by this one block. Okay, now if you concentrate on this one natural rubber as well as this one felt, so whatever the resistance comes for the motion of this block in downward direction or machine in downward direction, okay, so that resistance we can just consider that resistance in terms of stiffness, okay, by natural rubber as well as next one is nothing but by the felt. Okay, so similarly the resistance comes in terms of its motion. Okay, so you can just consider that resistance in terms of damper. Okay, so one damper is damper comes for this one natural rubber as well as for the next one is damper come for the next one felt. So this is nothing but the mathematical model for this physical system. Okay, so equivalent mathematical model we can just get like this one. I just consider k1 k2 or and just say suffix for this one rubber as r, suffix for this one is nothing but f. In this case we can just give the suffix as r and here f, like this one. So what's about the equivalent, again a model for this one. So mass term with us here. So equivalent stiffness can represent by single spring like this one and equivalent damping coefficient by single damper. I will just give the suffix for this one as C equivalent and here K equivalent. Okay, so in this way I can get the mathematical model for this physical system. All the data available with us, the mass with us 20 kilogram. Okay, and then apart from this one kr, cr, kf, cf, these values with us. Okay, so by considering both the springs are connected in series, this one dampers are connected in the series. Okay, so first of all get the equivalent stiffness for this system, okay, as well as equivalent damping coefficient, okay, available in the given system. For that, if you look towards the given data, I'll just write that given data here. The value of the mass with us given mass with us 20 kilogram. Next to this, kr is given. Here the value of the kr with us 3000 newton meter. Next, kr with us 100 newton second meter. Next one, kf with us 12000 newton per meter. Next one, cf with us 330 newton second per meter. Okay, so in this way the data with us. So to find the values for this one, undamped and damped natural frequencies. Okay, so undamped means what are the natural frequency of the given system, okay, as it is without damping. Okay, so for the springs connected in the series and dampers connected in the series, so we can write the relation for this one. For springs and dampers in series, you can get the equivalent stiffness for the springs connected in the series like this one. First one, the resistance occurs by the rubber. Okay, in terms of its stiffness, you can just write here 1 upon k1 kr plus 1 upon kf for the field. Okay, so already the values with us, just substitute here. The kr value with us 3000. Next to this one, kf value with us 12000. Okay, after solving this, you can get the value for k equivalent equals to 124 newton per meter. Similarly, you can get the equivalent damping coefficient involved in the system like this one. 1 upon c equivalent equals to 1 upon cr plus 1 upon cf like this one. The values for cr and this one cf already with us. Cr is here and cf is here. Just substitute here. Cr 100 plus 1 upon 330. Okay, solve this and get the value for c equivalent. C equivalent equals to 76.75 newton meter. So once the value for k equivalent and c equivalent with us, our next task become very easy. So easily you can get, and here is this portion. Just carry this term c k equivalent and this second term here. So in this way the two values with us. Okay, now we know the relation for natural frequency. Natural frequency, we know omega n equals to square root of k by n. So this k is nothing but the k equivalent. Okay, so what's about this k equivalent value? Already this one with us. Just substitute in the given relation 2400 by mass with us 20 kilogram. If you simplify this one, what do we get here? 10.954 radian per second like this. Okay, now next one, next term is nothing but zeta. Okay, so what's about the zeta? Zeta is nothing but c equivalent divided by 2 into k equivalent into m. So already I have seen this relation in the previous problem. Okay, so c is nothing but 2 into square root of k into m multiplied by zeta is nothing but the c term. Okay, so c equivalent only here written because the total damping coefficient available in the system is, okay, 76.75 newton this one newton second per meter in this way. So what's about this one? Just substitute the value for C equivalent 76 point this one 75 divided by 2 into K equivalent. K equivalent term with us 2400 multiply by mass term with us 20. So easily we can get the value for zeta. So once we get the value for zeta, our task become very easy. Okay. So omega d is nothing but omega n into 1 upon sorry omega n into square root of 1 minus zeta square. Okay, this is the relation with us. So what's about the omega n? Already value for the omega n is available with us here. Okay, so 10.954 multiplied by this one square root of 1 minus zeta square. So zeta value already with us 0.75, a square of this one. So after simplifying this, what we get? Can get omega d equals to 10.785 radian per second. Let us start next problem. For the arrangement shown in figure, first determine the differential equation of motion. Also determine the natural frequency of damped vibrations and the damping ratio for the system. If the system is modified to that as shown in figure 2, okay, so here is the figure number 1 and here is the figure number 2. Okay, hence or otherwise determine the value of damping coefficient for the system to be critically damped. So first of all, whatever the system given, okay, first system with us here. First of all, we'll draw the free body diagram of the given system. So first of all, assume that the system is moved in downward direction. Okay, so the displacement of this bob will take place like this one. So the bob will displace by angle theta. Will show that angle, okay, here theta. Okay, so at the same time the different forces are acting. So whatever the this one bob comes in downward direction. Okay, because of this, so what's about this one? This indicate the spring force. Okay, so spring force acts in upward direction. For that, I'll just say this displacement nothing but the y. So k multiplied by y is nothing but the spring force here. Similarly, for this one, whatever the displacement comes for this damper, just say that displacement is nothing but the x displacement. Okay, so if x is the displacement, what's about the damping force comes here? Whole system moves in downward direction. Okay, means whatever the force comes in upward direction is nothing but the c multiplied by x single dot. Okay, so what's about the accelerating force? As per our discussion during the first topic, accelerating force comes in the direction of motion of particular system. So accelerating force comes in the direction of motion of this pendulum. At the same time, one spring is attached here. So the spring force is nothing but here k multiplied by y. Here y is displacement, so k multiplied by y is nothing but the spring force. Similarly, x is displacement with respect to this damper, so its velocity is nothing but x single dot. Okay, so x single dot indicate its velocity. So damping coefficient c multiplied by velocity is nothing but the damping force. See the tendency of this one in move to move in downward direction. So this force must be in opposite direction of its motion. So the value in front of you c multiplied by x single dot. Okay, so let us start for the development of differential equation. So before that, it is very important to know the relation for the linear displacement occurred during the spring and here at the place of damper. Okay, so let the mass is displaced by an angle theta. If you just consider this one, the mass, okay, is displaced by angle theta. The spring deflects by a linear distance, this one y, and the damper displaces by a linear distance x, such that we'll just say the relation x equals to. So what's about this x distance? Okay, if you consider this small triangle, this triangle form here. Okay, so what's about this x? For the smaller triangle, this angle, so what's about this relation? You can just say simply theta multiplied by b, as angle is very small, so we can just say theta multiplied by b. Okay, similarly, what's about the y? Y is, for to get the value for the y, if I consider this triangle. Okay, so simply can just write this y is nothing but or from this triangle I can write the relation for the y and this one theta. Tan of theta equals to this side divided by this side. Okay, for the smaller angle you can just say that tan theta equals to theta, and we can get that relation for the y like this one, y equals to a into theta. So if you look towards this term, okay, what do we get? X equals to ab and y equals to this one, sorry, x equals to theta into b and y equals to a into theta, like this. Okay, so what's about the spring force? So spring force, already we have seen here, the spring force is nothing but here k multiplied by y. Okay, and what's about the damping force? So damping force is nothing but here c multiplied by x single dot. Okay, c multiplied by x single dot. So k multiplied by, what's about the y term? So already the information about this y with us, a into theta, just substitute here. Okay, like this. So we can get the spring force is nothing but k into a into theta. So what's about x single dot? Now if we differentiate this relation with respect to this one time t, so what do we get here? We can get that relation in this way: c x dot here is nothing but the theta single dot multiplied by b, like this. Okay, or we can just simply write cb multiplied by theta single dot. Now apply the Newton's second law of motion for this one, for the various forces. What's about the Newton's second law of motion? Applying Newton's second law of motion. We know the Newton's second law of motion: accelerating force equals to summation of external forces. Okay, so in this case, accelerating force with us, if you concentrate on this one, so whatever the force comes in the direction of motion of this bob is nothing but the accelerating force, whose magnitude is nothing but I into theta double dot. Why I consider this one I into theta double dot? Because this is the circular motion. Okay, so if you look towards the direction, this turns about this point in clockwise direction. So as per our notation, we have to give the minus sign for this one. Now just focus on this spring force. So ky is nothing but here spring force. So already that relation with us, ka multiplied by theta. This is the spring force. Okay, don't confuse. Okay, here ka multiplied by this one theta. Thus this a theta term is nothing but the y term. So ky is nothing but the spring force. You have to take the moment of this spring force about this point. Okay, so ky multiplied by a. So ky already with us, k multiplied by a theta. Again you have to multiply by that term by a term. Why? Because you have to take the moment of this force about this point. Okay, so this turns about this point in anti-clockwise direction. For anti-clockwise you have to do the plus sign. Okay, again you have to take the moment of this damping force about this point. So what's about this one damping force with us? C multiplied by x single dot. Okay, this is the damping force with us. You have to take the moment of this force about this point. Okay, so perpendicular distance with us a. So again this force turns about this point in which direction? In anti-clockwise direction. For anti-clockwise you have to use the plus sign, and this magnitude already with us. C x single dot means here CB into theta single dot. So CB into theta single dot multiply by this one, this distance B. I hope this step clear to you. Okay. So here for the concentrated mass, we know the value for I. I is nothing but the ml square. Okay. Now we'll just modify this or write this equation in a such way that we can get the next step. So just replace this I term by ml square and take all the terms towards the one side. Okay, so everything will become now positive. So k multiplied by a means a square into theta plus c multiplied by this one b multiplied by b square into theta single dot, okay, equals to 0. So towards the right side the 0 will come. Okay, so what's about the next one? So equation number 1. So this equation number 1, what this equation indicate? This term, okay, this term and this term. I'll just simply rearrange this equation in a such way that we can get the various terms. Okay, I'll write this first term here, a square into theta equals to 0. So giving equation number 1 for this one, I'll give equation number 1 for this. Okay, so what's about this equation? Equation number 1 is nothing but here equation 1 can be written as I means this term. Okay, so I into theta double dot plus ct into theta single dot plus kt into theta equals to 0. Now you can easily identify the various term. Okay, where, so if we compare equation number 1 and equation number 2, what do we get here? Just compare equation number 1 and equation number 2. So where I is nothing but, what's about the I? Just compare this I here. Okay, so mass term with us, I is nothing but here ml square. Okay, in this we can get the value for I. So what's about the ct? Ct is nothing but cb square. Ct equals to cb square. What's about the kt? Kt is nothing but ca square. This one, kt is nothing but ka square. Okay, so as per definition, what's about the omega n? Omega n in is nothing but square root of kt divided by I. So already the kt term with us, kt term with us, I term with us. Just substitute the value of kt here. So ka square divided by ml square, like this one. So what's about the next one? So equation number this one to be critically damped. Okay, to represent this equation number 1 as a critically damped system, we have to introduce this term. Okay, cct equals to 2 into square root of kt into I. So already we have seen this relation. Cc is nothing but 2 into square root of k into m. Okay, so here k term is nothing but kt, m term is nothing but the I term. Okay, so already the value for the kt with us. Kt, what's about the kt? kt kt is nothing but here ka square, ka square, and what's about the I is nothing but the ml square. Okay, I hope visible to you. Okay, so in the next step, just simplify the term, okay, and get the next relation. Okay, so I'll erase this portion. Now look towards this one. A square and L square terms are inside of square root sign. Okay, so easily we can take that both the term in outside of that square root sign. Okay, like this one, a into L will come square root of only k into m term will remain. Uh, this one k and m, okay, terms will remain inside of the square root sign. Okay, now what's about the zeta? So zeta is nothing but is the ratio of actual damping coefficient to the critical damping coefficient. As the torsional term is involved in the system, so ct divided by cct, okay, relation will come for this zeta. So what's about the ct value already with us, ct with us here cb square. So cb square divided by cct is nothing but 2al into square root of k into m. Okay, next one, the damped natural frequency would be, so my aim is to get the damped natural frequency for the this one first case. Okay, also determine the natural frequency of the damped vibration and the damping ratio of the system. Okay, so my aim is to get the damped natural frequency. Okay, so the damped natural frequency would be omega d equals to omega n into square root of 1 minus zeta square. Okay, so that's why the value for the zeta or relation for this zeta we have earlier calculated. Okay, so if I take this omega n inside of the bracket, okay, the relation will changes like this one, omega n square into omega n square into zeta square, like this one. Now omega n, this term already with us, this one omega n. So just simplify for the omega d equals to omega n. Omega n is nothing but root of a square divided by ml square minus once again omega n is nothing but same term ka square divided by ml square. Okay, like this, multiply by zeta term is here. Okay, in this way the zeta term with us, you have to take the square of this zeta. Okay, so c square into b raised to 4 will come the square of this, okay, term zeta square is here, so square of this one is c square b raised to 4 divided by the square of this one 2 is nothing but 4 square of this a square l square, and square of this one, the square root sign will vanish here, like this one. Okay, so in the next step again simplify for the this one. Okay, so this term, now from this term if you look towards here, okay, so this one k square for this one omega n. Okay, and this one ml square. Okay, this term as it is in the denominator, so zeta value already with us here. Okay, so in the next step if you look towards this relation, k get cancelled. Okay, now from this term and this term we can easily take this one a square by l square as common. Okay, a square by l square, here a square by l square term with us. Or before that, if you just see in the next step, what is the written here? A square b raised to 4 divided by 4 a square. Okay, so instead of cancelling this a square term, just write this a square term as it is. Okay, so here we can easily take this a square by a square, a square by 1 l square term, okay, as common. Now just see here in the next step, what do we get here? We can easily take this a by l, a square by l common means here again, if you just take the outside of square root sign, okay, so the a by l term will come. So instead of the square root sign, here the k by m term will remain, and just see in the next part, c square into b raised to 4 divided by 4, 1 l square already taken common, so l square will remain here, l square, l square into m square into a square. Okay, so in this way the damp natural frequency relation we get it. Now the second point, determine the value of the damping coefficient for the system to be critically damped. Okay, second system is the same system, okay, in front of you. When the position of this one damper is changed from its next position to this position. Okay, so here the stiffness is given, then damping coefficient. Okay, this one you have to do calculation for this one, damping coefficient. Okay, so here uh, value for the mass with us, then the various distance is also given. Okay, now what's about the second point? If you look towards the second point, we'll just continue that second point here. I hope this one gap natural frequency for the first case clear to you. Okay, so with respect to second system, start our discussion. So for critically damped system, so we know for the critical damped system. Okay, so what's about the value for cc? In this case, c must be equals to cc must be equals to c, and the value for zeta must be equals to 1 for critical damped system. Okay, so already I studied during the discussion of that derivation. So in this case, what we get here, ct equals to cc into 2 in cct. Okay, like this one you can get a relation. Okay, so what's about this cct? So already this term, so cct and this one ct term already we have solved in the previous step. Okay, so what's about this ct? Ct is nothing but here, ct is nothing but cb square. Okay, just go through our previous steps. Okay, cb square for this ct, and what's about the cct? Cct is nothing but 2 into a into l into square root of k into m. This relation already with us. Okay, thus for the system to be critically damped, the linear damper should be have a damping coefficient of this one cc. What's about this cc? Now see this step, cb square equals to 2a into l into square root of k into m. Okay, so what's about this cc? Cc is nothing but 2 into a into l into square root of k into square root of k into m. Okay, this term with us here, the b square term goes in denominator like this. Now see the different values with us. What's about this 2 multiplied by a multiplied by l into square root of k by m? What's about this b? So if you look towards this one, b and a distance, the position of this damper is now changed, okay, to this position. Okay, means whatever the a distance and b distance becomes same, since the value of a equals to b. So can I replace this B by A? So can easily replace this one like this, A square. So if I replace this one B by A term, so 1A get cancel. What's about the remaining term? CC equals to 2L. Okay, 2 multiplied by this one L into square root of K M by A. So all the values with us. Just substitute here 2 multiplied by L. So what's about the length of this one? Length of this pendulum 170 mm. Okay, with us. Not this one into meter by multiplying 10 raised to minus 3. Okay, multiply by this one root of K into M. So what's about the value of K? This one 6000 Newton meter. So already given. Okay, multiply by 2 kg mass is given for this bob. Okay, so 2 kg divided by, so what's about the A 75 mm, so 75 multiplied by 10 raised to minus 3 like this. So in this way you can get this step. Okay, so after solving, so what we get here, CC equals to 496.602 Newton second per meter.